Hello there, POEers, and welcome back to another exciting video on, this one's going to be on external reaction forces. Up to now we've done our vector calculations, and now we want to start to look at some actual structures such as this beam and determine what kind of forces are being felt at the different areas in this beam. All right, so first of all, you can see this beam is supported by a pinned support and a roller support. We have a 30-pound force pressing on it right here, approximately 6 feet away from the pinned end. We have a 45-pound force pushing down here, 3 feet away from the other force. And we have 6, 3, 4, our whole beam is 10 feet long. So if you think about it, first thing to do is think about it logically. What do you think is going to be feeling more forces? Here at this point or at this point? Well, hopefully, if I could have my two assistants up here right now. And here we have a beam, and we're going to have an assistant right here holding that, and an assistant right there holding that. And so if I have two weights, and I put one approximately a little over halfway towards that end. Are you ready, assistants? And then I take, actually, I'm going to put the smaller weight there. And then I take a heavier weight and almost place it at this end. Which point? Point A or point B is going to be feeling more force? Well, hopefully, just from common sense, we're thinking point B is going to be feeling a whole lot more force here, just because of the way the weight is distributed. So when our calculations are finished, hopefully they verify that. If they don't, we probably have an issue and we got to go back and check our calculations. Thank you, lovely assistants. So there's three key formulas that we have to use to figure out the external forces that are acting on this thing. The external reaction forces. Okay? They are, some of the forces in the x have to be equal to 0, some of the forces in the y have to be equal to 0, and some of the moments have to be equal to 0. So to start with, we're going to get rid of these two supports and replace them with our reaction forces. So let's see, I think I'll use blue for that. So first of all, I'll get rid of this pin support. And remember, pin supports can feel forces in both the x and the y direction. So we have forces working on this in the x, forces in the y. We're going to call this the force at x in the y. I'm sorry, let's change that. We'll call this point A. The force is at A in the y direction, and the force is at A in the x direction. Both of the directions are there because it's a pin support. On this end, we have a roller support. And remember, rollers are made so that the structure can actually move on the x-axis with theoretically no friction. So there is no x force here, but there certainly is a normal force reacting to the weight coming down on it. So the only force you have on the roller is, we'll call this point B, a force B in the y. All right? So there are external reaction forces to these forces that are pressing down onto the beam. So we take a look at our first equation. It says the forces in the x have to equal 0. And then we take a step back and we look at what forces are working on this beam in the x dimension. Well, there is only one over here, FAX. So according to our formula, FAX has to be equal to 0 because there's only one there. So FAX is already solved. It's 0. Then we have to look at forces in the y. Well, now it gets a little more interesting because we actually have 4 forces working on this at the y. Now, you want to pick the point that you want to consider your measurements coming from. And we could either start at point A or point B. Always start at the one that has more forces acting on it. And you'll see why in a moment. So we're going to call this where we're going to take all our measurements from right here. All right? So what we're going to do is look at y, and we're going to say, well, let's see. FAY, that's a force, plus FBY. And now we look at these guys that are coming down. They're going to be negative forces, minus 30, minus 45. All those forces have to add up to 0. So we can go ahead and start simplifying it, but you see we soon run into a problem because we say, well, FAY plus FBY is equal to, if we add those together, 75, we add them to both sides, 75. And we have a problem here because we have two variables. So we can't solve for this yet because we don't have enough information at this point. So we have to sort of set aside right now the forces in the y, and we're going to move to the moments. Now, we chose this as our starting point, and we're going to measure everything from point A. All right? So the nice thing is, if you think about these two forces, they are 0 distance away from themselves. And moments are forces times distance. So since the distance away from itself is 0, we don't have to worry about these at all. But what we do have to worry about is this force, and this force. So I'm going to try to draw this over here. Hopefully you'll be able to see it. So sum of the moments has to equal 0. Well, the first moment is 30. And a moment is force times distance. So we're going to say, well, it's 30 times 6. When you're doing a moment, you have to remember which direction it's going to know if it's a positive or negative number. And you use your right-hand rule, and you curl your fingers, and you say, well, that one is going down, but it's pivoting around this point. So if I do that to make it go that direction, that's going to be a negative number. It's going clockwise. That's a negative number. Okay? I move over to the next one, which is 45 pounds of force. It's also going to be a negative number. And we're going to multiply that by its distance away from A, which is 9. And now we come to our next force, which is FBY, and that is going up, and it is 10 feet away. But we don't know what that force is at this point, and I hope I'm probably going off the board here. That's going to be a positive number because it's going counterclockwise. And again, if we use our right-hand rule, we can go, oh yes, my thumb is pointing towards me. And so that is FBY times 10. And now I can go home and simplify that. I have minus 180 minus 45. Let's see, 9 times 50 would be 450 minus 45 more would be, I should have done this one ahead of time, 450, 405? Check me out, somebody, while I'm doing this. I think it's 405 plus FBY times 10. So if my calculation on right, I'm waiting for my verification of my number here, minus 180 and minus, so 9 times 45 for me, Drew.
Negative 405.
Negative 405, cool. So 180 and minus 180 minus 1 is 585 minus 585 plus FBY times 10. All this has to equals 0. So now I can add the 585 to both sides to simplify, and I get FBY times 10 is equal to 585. I divide both sides by 10, and FBY is equivalent to 58.5, I hope. Okay, so now we've calculated for FBY, and I'm waiting for my verification. I think that's all right. 585 divided by 10 is 5. Good. Oh, now we can come back over here. Well, first of all, there's my FBY. Now I can come back over to here. And I have solved for 0, so that's going to be 0. So now I can say FAY plus FBY, which is 58.5, is equal to 75. FAY minus the 58.5 on both sides. 75 minus 58.5 is 16.5. So at this point, if I can look at this thing, I can say, well, FBY, this force right here, is supporting 58.5 pounds. This force at point A is supporting 16.5 pounds. And so those are my two reaction forces, and hopefully the numbers are correct, but the first thing I think is, does that make sense? All the weight shifted towards this end. Should FBY feeling more force than FAY, just like our two lovely assistants up here? And yes, it is feeling a whole lot more force, which makes good common sense. So that's how you solve for the two reaction forces in that example.